A prime number is an integer p strictly larger than 1 whose only positive divisors are 1 and itself. So for example, 2, 3, 5, 7, 11, 13, 17, and so on are prime numbers. So the number 2 is prime because the only positive divisors are 1 and 2. So only himself and 1 divide him. There's no other number, positive number greater than 1 that divides 2, right? So 3, the same. 2 doesn't divide 3. 5, the same. No number, only 5 and 1 divide 5, and 7, and so on. On the other hand, an integer which is greater than 1 is composite if it is not prime. And so this means that it has positive divisors other than 1 in itself. So some examples are like 4, 6, 8, 9, 10. And so for example, 4, you can write it at 2 times 2. And this means that not only 4 divides 4 and 1 divides 4, but also 2 divides 4, right? Same for 6. You can write it as 2 times 3. 9, you can write it as 3 times 3. And so every number that is composite is going to have some divisor that is different than 1 and itself, right? And so prime numbers are the numbers that cannot be broken into smaller positive factors, while composite numbers can be. And so one small point, which is quite important sometimes, is that we don't usually define the number 1 to be either prime or composite. And the reason for that is when we later see prime factorizations, this is so that prime factorizations are unique. So like we said here, 6 is equal to 2 times 3. And apart from just permuting these two numbers, this is the only way you can write 6 as a product of primes. If you allowed for 1, then you could write 6 like this, but you could also write 6 like this, right? And so 1 is able to pop up many times, and it sort of messes up the theorem a bit. So it's usual that you do not define the number 1 as either prime or composite. Okay, and so now we're gonna show one of the most important, or one of the most famous results in math, which is that there are infinitely many primes, right? And so this proof goes back to Euclid, and we're gonna do a proof by contradiction. So let's do a proof. And so by contradiction, or at least let's sketch out the proof here. And so the idea is, so how do we do proof by contradiction? We suppose that what we want to prove is not true, and then we try to find some contradiction. So suppose there are finite, let me erase this, there are finitely many primes. So suppose you have a finite amount of primes. So there's a prime 1 all the way to prime n. So suppose you have n primes, right? So there's the first one, the second, and up to n, and they're only a finite amount. Now, consider the integer. So consider the positive integer, I guess, also. Let's use a different letter. M equal to, you multiply all these prime numbers. So let's write it more explicit. P1 times P2 times P3 all the way to Pn. So multiply all these numbers and add 1 to it. Okay. Okay. So now when we divide this number by any Pi, so when we divide M by any Pi, notice that we get a remainder of 1, because I mean this is exactly what's written here. For any Pi, you're writing M as something times Pi plus a remainder 1, so you're going to have a remainder of 1. So the remainder is 1, which means that no prime, so what this means is that no prime in our list divides M, right? So if you look at the number M here, every prime, you can't write it as, you can't write M as something times that prime because you always have a remainder here. So none of those primes divide M. So thus, from that, you can conclude two things, right? Either M has to be prime, either M is prime, but that's a contradiction. So because if M is prime, he should be on this list, and he's not on this list because we constructed him as he's different from everyone on this list. Every number here is different from this number here. So this is a contradiction. And the other is that, well, then M has a prime divisor not on the list. But this is a contradiction, again, because we're assuming that this is the list of all of them. So M has to have some divisor that is not there, but so because either M is prime, but then he would be in the list, or if M is not prime, then he has to have another divisor, and that's just not possible because it would be someone that's not on the list. So in either case, we get a contradiction. And so this means that it cannot be true that there are finitely many primes, so there has to be an infinite amount of prime numbers.